Okay, here we go again. First things first, I am against energy drinks. These are not healthy. But it is what it is. So, number 15. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. That's wonderful. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution, with mean 27, standard deviation 0.8. When medium is chosen, the amount of liquid M dispensed is normal, with mean 17 and standard deviation of 1/2. To test the manufacturer's claim, the restaurant manager measures the amount of liquid, 20 cups, fill with the large setting, 25 cups, fill with the medium setting. Oh, wow. Okay, so what is the shape of the sampling distribution of a large cup minus a medium cup? So the amount of liquid in each cup. So basically, you take a cup, you fill it, measure the amount, take another cup, you fill it, measure the amount, subtract the difference, plot it. Boom, boom, subtract, plot. What's that graph going to look like? If you did it, an infinite amount of times, the sampling distribution. So the shape is normal because both pops are normal. The mean, that could be the corona, I have no idea. The mean is this, so 27 minus 17, which is 10, and the standard deviation is sigma squared over n plus variance over n square root, and we're going to get 0.8, because that's the standard deviation, 0.5, that's the other one, squared, 0.205. All right, next. How did that happen? That's really gonna throw me off. 16, the Wade Tract Preserve. Has anybody ever been there? I have not, but right now it sounds like a great place to go. It's an old growth forest of longleaf pines that has survived a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is, how do the sizes of the longleaf pine trees in the northern and southern halves of the forest compare? So this looks like the north, and that's the south. A civil war amongst the pine trees. And this is what it looks like. This looks to be skewed right. This looks skewed left. But these are the sample graphs. So the researchers took a random sample of 30 trees from each half. See, 30 trees from each half. Measured the diameter at breast height, dBH, in centimeters. Yeah. Here are the comparative box plots of the data and summary statistics from Minitab. Construct and interpret a 90% confidence interval for the difference, and then mean diameter breast height of the longleaf pines in the northern and southern halves. Now, this question I got out of the book. Most of these questions are in the book, so I kind of just cut and paste the examples. So, because I only had like an hour in my building to kind of put all this stuff together. All right, so we've got to do a confidence interval. All right, state. 90% confidence interval to estimate P1, no, sorry, mu1 minus mu2. Okay, next is now, on the AP, you should state somewhere, even with P's, what the parameters are. Where like mu1 is the true mean dBH for the north, mu2 for the south, so forth and so on. You should state the parameters somewhere in the problem. The AP likes it up here, but if you state them in your conclusion somewhere, I'm sure you'll be fine. Plants, so it's a 2-sample T interval. Let's see. 4 mut 1 minus mut 2. And the conditions are, so it's got to be random. So the data came from independent random samples of 30 trees. So there's 2 independent samples of n equals 30 from each. Need to say independent. Of course, they have to be independent. I mean, how could a tree be growing in the north and in the south? That would be a magical tree, unless if it was right on the border, for which that's more of a philosophical question. I'll let you guys think of that. 10%, so as long, 10%, so as long as there are 300 in each, and then number 3. What's number 3? It says normal. Let me see here. No, it doesn't say normal, but n is greater than or equal to 30, so that's kind of going to be okay. So n1 greater than 30, n2 greater than 30, and those box plots give us no reason to doubt normality of the populations. So this is going to be approximately normal. I mean, yeah, they're skewed, but it just, as long as it's not an insane amount of skew or a lot of heavy outliers. All right, so we got the plan. Now we got to do the do. And you know what? From right here, we're going to do, let's see, stat, test, 2-sample, we need a T interval. Where are you? Right here. So 2-sample T int. All right, so let's just put in the data. So x1. Oh, we're going to do north minus south. So, all right, we did state that somewhere. 23.7, 17.5, 34.53, 14.26. Right, no. 23.7. Oh, 30. And 90. No pool. Never pool with means. Write that down somewhere. Never pool with means. Calculate. Here it is. So that's the degree of freedom, and that's the confidence interval. And yeah. So, but honestly, I really hate negative confidence intervals. So I think I would do this in reverse, because I think it would just make more, it would almost make more sense, because the south is bigger. It's just easier to interpret those variables. So who cares? South, and let that be north. I'm going to flip-flop these. Of course, I'm going to change this. 5.3, 14.26, 30, 23.7, 17.5, 30. All right, a little bit easier. But x bar 1 minus x bar 2 plus or minus t critical value, and then s1 squared n1 plus s2 squared n2. But you got to be careful when you do the critical value, because you're using this degree of freedom. This degree of freedom produces this interval. See, if I do inverse t, it's 90%, so I get this. 55. Let's see what we get. Inverse t, 0.05, 50. Yeah, well, 1.67. But if I do inverse t, the smaller of one of these, 0.0529, I get plus or minus 1.70. That actually shouldn't be 55. You should have the whole decimal. But notice this value stretches out the interval more. It's a conservative estimate. But this is the real deal. So if you write this value here, your interval is not going to be the same as the calculator. So just know that. All right, let's go back. To sample t interval, right? All right, so we are 90%. That's the interpretation. I mean, so this interval would suggest so that's it. Okay, good. I'm going to skip 17. Let's go to 18. All right. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for black men. Such observational studies do not establish causation. Right, observational studies, if you remember, they can give you associations, they can tell you the risk, your odds, but only actually, what can establish causation? Anybody? Anybody? Let's see. Yes, Brittany. Good experiments, very nice. Researchers therefore designed a randomized comparative experiment. All right. Subjects, 21 healthy black men who volunteered to take part in the experiment, they were randomly assigned to two groups. So 10 of the men got the calcium for 2 weeks, while the control group of 11 received a placebo that looked identical. The experiment was double-blind. The response variable is the decrease in the systolic blood pressure for a subject after 12 weeks in millimeters of mercury, of course. An increase an increase appears as a negative number. Nope. Here are the data. All right. Calcium group. An increase appears as a negative. All right, so this person on calcium, not too good. Or no, yeah, you want to lower it. Okay, so yeah, that person was good, good, good. All right, so do the data provide convincing evidence that the supplement reduces the pressure more than the placebo? Well, is calcium reducing it more than the placebo? Well, okay, so now we got to do a hypothesis test. So we have state so mu1 minus mu2 equals 0. So I'm gonna let the calcium be 1, the placebo be 2. If you switch them, the answer's still good, but sometimes you have to word it a little bit differently. And then HA, mu1 minus mu2, so greater than 0. Actually decrease. We got to do greater because an increase is negative. So then that's why we would do that. A decrease, therefore, would be a positive number. All right, so now plan, we're going to do 2 sample t-test for mu1 minus mu2. So now we got to do the same conditions, okay? So we're going to do, this is an experiment, so they have to be randomly assigned to both groups, which they are. You don't need the 10%. And then for this one, since N1, N2 are both less than 30, the sample graphs, you're going to use the sample graphs to then determine what you would. These sample graphs look like they're okay. There's no outliers, there's no skew, so the populations are good enough to use normality. Okay, so now we need a test stat here. And we're using T because we always use T's with means. Square root. From here, so a 2 sample t-test. 2 sample t-test. Data would be if you had it, like you put all of these in L1, actually, which we have to do. So, all right, L1, 7, -4, 18, 17, -3, -5, 1, 10, 11, -2. All right. Yeah, so L1, L2, the frequencies are 1 because we're not doubling it, and this symbol is facing that way. Never pull. Never, ever, never pull. Write that down 4 times. All right. So we get this value. But the calculator gives you the means, so you could actually copy these values from the calculator, you know. See, so we get 5 minus 0.27 minus 0, 8.7 squared over 10 plus 5.9 squared over 11 square root, and we get 1.604. Do you have to input these values? No. The AP says as long as you write it by either the formula or the name, you're good to go. So, p-value, that is the probability that your test stat is greater than or equal to, or greater than, whatever you found. So that's TCDF, 1.604, 99. Now, the p-value in here used that degree of freedom. The smaller of n1 minus 1, that would mean 9 and 10 for these degrees of freedom. So if you're going to say 9 and put that here, it's going to alter your p-value slightly, not giving you the same answer as the calculator. Okay, so since p-value is greater than alpha, we failed to reject HO. So this experiment doesn't provide that the true mean in systolic blood pressure Okay, there we have it. Not going to worry about that. I'm going to stop here.